So, good day, Melbourne. I'm Dave Aronson, the T-Rex of Codosaurus, and I flew all the way down here on my pet pterodactyl to teach you to kill mutants. But first, a bit of a caveat. I do not consider myself an expert on mutation testing. I've used it a little bit, read more about it, discussed it a little with the real experts, the people who write the tools, but I don't consider myself an expert. But one of the dirty little secrets of public speaking, including at conferences, is that you don't need to be an expert on your topic. You just need to know a little bit more than your audience, enough to make it worth their time to listen to you, and be able to convey it to them. And mutation testing is still so rare that most developers haven't even heard of it. So let's start with the very basics. What on infinite earths is mutation testing? In our universe, that of software development, not comic books, graphic novels, it's a software testing technique. Surprise! But what makes this technique different from all the other techniques? The big difference is that most of the others are about checking whether our code is correct. Mutation testing, however, assumes that our code is already correct, at least in the sense of passing its tests, which means it also assumes that we have tests. Mutation testing instead is looking for not just one, but actually two other properties. And in my opinion, the more interesting and usually immediately helpful of these is that our test suite is strict. Now, you might be thinking, isn't that what test coverage is for? If we have 100% coverage, doesn't that mean that our code is fully tested? No. The only thing that coverage tells us is that at least one test executed the code that it claims is covered, the stuff shown usually in green, and that no tests executed the stuff that it doesn't claim is covered, usually shown in red. It tells us nothing about whether the correctness of the code had anything to do with the passing or failing of any particular test. By way of illustration, let's look at a test and comment out the assertion. Now, assertions might be commented out or actually removed, maybe not even written in the first place, for any number of reasons, usually not very good, but it happens anyway. We run the function, so it still shows up as covered, but we're not checking anything about it, so it's obviously not tested. This is just one of many, many ways in which coverage can be extremely misleading. So how can we tell if the correctness of the test had anything to, the correctness of the code had anything to do with the passing of the test? That is where mutation testing comes in. To check that our test suite is strict, a mutation testing tool will try to find the gaps that let our code get away with unintended behavior. Once we find these gaps, we can fill them in by either adding more tests or by expanding and improving any existing tests. Lack of strictness usually comes from lack of tests, of course, but also poorly written tests or tests that have been poorly maintained, like they didn't keep pace with changes in the code. Speaking of which, the other thing that mutation testing checks for is that our code is meaningful, by which I mean that any tiny little change, within reason, to the code will have a noticeable effect on the code's behavior. Lack of meaning usually comes from code being unreachable or redundant or otherwise just not having any real effect. Once we find meaningless code, we can either make it meaningful, such as eliminating a redundancy, or we can just remove it. Mutation testing puts these two together by ensuring that every tiny little change it knows how to do has a noticeable effect on the code's behavior and that our test suite is strict enough to notice that change and fail. Now, not all the tests have to fail, but each change should make at least one test fail. Now that's the positive side, but there are some drawbacks. As Fred Brooks told us back in 1986, there's no silver bullet. Besides, those are for taking care of werewolves, not mutants. The first drawback is that it's rather hard labor on the CPU, and therefore usually pretty slow. We certainly won't want to mutation test our entire code base every time we save a file. Maybe we can do it over a lunch break for a smallish system or over a weekend for a larger one. Fortunately, most of the tools do have ways to tell it only test function or this module or this file, maybe multiple of those. And most of them also have some sort of incremental mode built in. So we can tell it, just test what has changed since the last time we ran the tool, or the last git commit, or the difference from the main branch. Between those sorts of filters, we can narrow it down to something we might be able to do on every file save if we save early, save often like we know we should, even if we don't always. Another drawback is that its CPU-intensive nature can really run up our bills on cloud systems like AWS or Azure, or however you pronounce it. It's also not at all a beginner-friendly technique. It tells us that some particular change to the code made no difference to the test results. But what does that mean? It takes a lot of thought to figure out what a surviving mutant is trying to tell us. Their accent is very strange, and they're almost as incoherent as zombies, but with a much larger vocabulary, so they're not always on about brains. They're usually trying to tell us that our code is meaningless or our tests are lax, or both, but it can be very difficult to figure out exactly how. Even worse, sometimes it's a false alarm, because a mutant might not have made any tests fail, but it didn't really make any difference to the behavior in the first place. But it can still take a lot of time and effort to figure that out. There's also quite a lot of code we just shouldn't bother to test. For instance, if we have a debugging trace that says the value of x is, and then the value of x, that constant part will get mutated, but we probably don't care about that. We almost certainly don't have a test for that. Fortunately, most of them do have ways to tell the tool, don't bother mutating this line, or again, this function, module, even whole file. But that's usually with comments, which can clutter up the code and make it a little less readable. So now that we've heard some pros and cons, how does this work? Unlike the bloke on this sign. It mutates copies of our code, hence the name. And it does this with the intent of creating test failures, otherwise known as faults. So mutation testing can be categorized as a fault-based testing technique. And this means it's sort of related to something you might already be familiar with, Chaos Monkey from Netflix. Just like Chaos Monkey helps Netflix spot errors and other such problems in their error recovery, mutation testing helps us spot problems in our test suite and our code. But the way mutation testing does this is sort of upside down from how Chaos Monkey works. Chaos Monkey is best known for injecting faults, such as dropped connections or increased latency, into Netflix's production network. If all still goes well, in the sense that Netflix's customers don't notice and the metrics still look good, then Netflix knows that their error recovery is working fine. Mutation testing, however, injects semantic changes, not necessarily problems. It doesn't know if these changes will cause problems or not. Now, we hope they all will, but that's up to the test suite. It injects them into copies of our code, not our actual network, and it does this in our test environment, not production. Whew. And if all still goes well, in the sense that our tests still pass, that does not mean that everything's good. That means there is a problem. Remember, every change should make at least one test fail. Mutation testing has also been compared to fuzzing, a security penetration technique involving throwing lots of data at an application. Mutation testing is sort of like fuzzing the code rather than fuzzing the data, and it's not random. Mutation testing tools usually have a set of mutations that they know how to do and what sort of points in the code they should apply it to. Now, some of the smarter ones can use the results of some simpler mutations to know they don't need to bother with some more complex ones, which can make it appear different when applied to different code bases, but it's still not random. But enough about differences from various things. What exactly does mutation testing do and how? Let's start with a high-level view. First, our tool breaks our code apart into pieces to test. Usually these will be our functions or our methods if we're using an object-oriented language, but I'm just going to stick with saying functions. Then for each function, it tries to find the tests that cover that function. If it can't find any, then most will simply skip this function. Better yet, they'll probably warn us that they're doing so, so we know we need to add some tests or possibly annotate some. More on that later. Some, however, will use the entire test suite, which is horribly inefficient because the vast majority of the tests it's running are not really relevant to this function. Now, assuming that we're not skipping the function in question, the next step is that the tool makes the mutants. And to do this, it looks closely at the function to see how it can be changed. And for each way the tool knows how to change that function, it'll make one mutant with that one little change. And once the tool is done making all the mutants it can from a given function, then it iterates over the list, and now we get to the heart of the concept. This chart represents the progress of our tool, and unfortunately the real-world tools don't generally give us quite all this information, let alone so nice and neatly organized, but it's a conceptual model that I use to help illustrate the point. So what happens is that for each mutant made from a given function, the tool runs the function's tests, but it runs them against the current mutant instead of the original function. If any test fails, this is called, in the standard industry terminology, killing the mutant. And now we take a bit of a detour. Some people object to this violent communication, especially since in the comic books, mutants are often metaphors for marginalized groups of people. And the tech industry is finally becoming more sensitive to such issues. I've been trying to come up with something a little nicer, like rescuing them or covering them or whatever, but the term of killing them is very well entrenched, and it's very difficult to change what people call something. So for this presentation, I'm just going to stick to the standard term of killing the mutant. So whatever we call it, it's a good thing, and it means that our code was meaningful enough that the tiny little change that our tool made in order to create this mutant did indeed have a noticeable effect on the code's behavior, and that our test suite is strict enough that at least one test noticed that difference and failed. After that happens, the tool will mark that mutant killed, stop running any more tests against it, and move on to the next one. Once a mutant has made one test fail, we generally don't care how many more it might make fail, like perhaps some of tests 6 through 10 for mutant number 1. Like so much in computers, we only care about ones and zeros. On the other claw, if a mutant lets all the tests pass, then it is said to have survived. And that means that this mutant has the superpower of mimicry, skilled enough to fool our tests. This generally means that our code is meaningless, or our tests are lax, or both, and now it's up to us to figure out exactly how. Now let's peel back one layer of the onion and look at some details of how this works. First, our tool parses our code, usually into an abstract syntax tree, so that this code becomes this abstract syntax tree. I'm going to assume that you're all familiar with the concept of an abstract syntax tree, or AST for short. We don't need to worry about understanding this one in detail, except to note that there are two subtrees rooted at def nodes, which means that those are defining functions. And yes, they have the same name in some languages. That's okay. This is in Elixir, and that's okay there. So after the tool creates the AST out of the code, then it traverses that tree, looking for smaller subtrees it can extract that represent our functions. Smaller things like branches, I guess you'd call them. And after finding them, it handles them basically as I described before, starting with looking for the tests. But how does it do that? That often relies on us developers either annotating tests, as I mentioned earlier, or using some sort of naming convention for the files and the tests. But these manual techniques are often supplemented and sometimes even totally replaced by the tool looking at what tests call what functions. That can get tricky and unreliable, especially when it's not called directly from the test. So after the tool has found the function's tests, then assuming we're not going to skip this function because it didn't find any tests, the tool makes the mutants. So how does it do that? To make mutants from an abstract syntax tree, it traverses that subtree just like it did to the whole thing. But now, instead of looking for even smaller subtrees it can extract, like twigs or something, I guess, now it's looking for nodes where it can change something. And for each time it finds one of those, and for each way it can change that node, it'll make a copy of the function subtree with just that one little change in it. For instance, suppose our tool has started traversing that AST, well, one of those AST subtrees I showed earlier, and has gotten down to this if statement. For every way it could change that one node, it would make a fresh copy of this whole AST subtree with just that one node changed in that one way. And after making as many mutants as it can, by mutating that one node, it'll continue traversing the tree to another node. And again, for each way it can change that node, it'll make a fresh copy of this whole subtree with just that node changed in that one way. And so on until it has finished traversing the entire function subtree. Now, I've been talking a lot about changing things and little mutations, but what kind of changes am I talking about? There are quite a lot. It could change a mathematical, logical, or bitwise, or other if you've got them, operator from one to another. So, for instance, x plus y could become x minus y. If the language and situation allows, it could change it to something of one of the other categories. For instance, in many languages, we could treat anything as Booleans. So, for instance, x times y could become x and y, or x exclusive bitwise or y. When the order of operands matters, such as in subtraction, division, exponentiation, and string concatenation, it can swap them. It could change a comparison from one to another. It could insert or remove a mathematical, logical, or bitwise negation. It can remove an entire statement It could remove an if condition so that something that might be either skipped around or done is always done. Similarly, it can remove a looping condition so that something that might be skipped around, done once, or done multiple times is always done once. It could replace a function's entire contents with just returning a constant, or returning one of the arguments, or raising a deliberate error, or nothing at all if the language permits. It could change a value to another value, such as by incrementing it or decrementing it or returning a constant. It could even return something, it could even change it to something of a completely different and potentially incompatible type, such as changing a number to a, if I may quote Smeagol, string or nothing. There are many, many other changes it can make, but I trust you get the idea by now. From here on, there are no more low-level details I want to add, so let's finally walk through an example. No, before we get to that, let's peel back one more layer of the onion and look at some pseudocode that sort of illustrates how it works. I'll give you a little time to take pictures. I'm not seeing anybody taking pictures, so okay, I'll just move on. Now let's walk through some examples, and we'll start with the very easy one. Suppose we have a function like this. Never mind why, it just makes a nice simple example, so let's roll with it. Think about what a mutant made from this function might return, since that's what our tests would almost certainly be looking at. It doesn't look like it would have any side effects. Mainly, it could return results such as these and many, many more, but I had to stop somewhere. Now suppose we had only one test, like so. Now this is a rather bad test, and I think why is fairly obvious to most of you. But even so, most of these mutants would get killed by this test, the ones shown here in crossed out green. The ones returning constants are quite unlikely to match. There's no particular reason a mutation testing tool would have the mutant return a 4 as opposed to, say, 0, 1, -1, or other significant numbers. Changing it to subtraction would get us 0, or a division would get us 1, and returning either argument alone would get us 2, and the incompatible types and deliberate errors would at least make the test not pass. But addition, multiplication, and exponentiation in the reverse order would still get us the correct answer. So mutants based on these mutations would survive our current test. So how do we see this happening? When we run a mutation testing tool, it gives us a report which would look kind of sort of like this. The exact words and amount of context and format and so forth will vary greatly depending exactly which tool we use, and as you'll see later, there are dozens if not hundreds. But semantically, the information it's giving us should be roughly the same, and to unpack that, what it's telling us is that if we change the function called power in file demo.ex, starting at line 42, in any of 4 different ways, then all its tests would still pass. And it goes on to tell us that those 4 ways are, first, to change the function declaration line to swap the arguments, and second and third, to change the one line that constitutes the body of the function, to change the exponentiation into addition or multiplication, or lastly, to change it to swap the operands of the exponentiation. So what is this set of surviving mutants trying to tell us? The very high-level message is that our test suite isn't very good, either because there just aren't very many tests, or the ones we have aren't very good, but we knew that. A common other thing that it could possibly be telling us is that we have redundant or unreachable code, but I think we can tell at a glance at the original code that That's very unlikely in this case. So the question boils down to, how are these mutants surviving? Are they pulling heists? Are they getting free room and board at the Xavier Institute? Or what? The usual answer is that they return the same value as the original function, or they have the same side effect, whatever it is our tests are looking at. To determine how that happens, it helps to take a closer look at one mutant and a test it passes. So let's start with the plus mutant. Looking at this change together with this test makes it pretty clear that this mutant survives because 2 plus 2 is the same, is equal to 2 to the 2. And so is 2 times 2, but he's in the background. We can save him for later. So how can we kill this mutant? In other words, make at least one test fail when run against that mutant with a test that would pass run against the original code. It's quite simple in this case. We just need to make at least one test use inputs such that x to the y is different from x plus y. For instance, we could add a test or tweak our existing test to something like this to assert that 2 to the 4th power is 16. 2 plus 4 is 6, not 16. So that kills the plus mutant. Better yet, 2 times 4 is 8, which is also not 16. We developers should know our powers of 2 at least that well. So this kills the times mutant as well. You'll often find that deliberately killing one mutant also kills others as well. However, the pair of argument swapping mutants still survive. But that's okay, we can attack them separately. No need to kill them all at once and be some kind of superhero about it. To kill them separately, we can, again, either add a test or improve our existing tests to something like this, to assert that 2 to the 3rd power, according to our power function, is 8. Now, if we reverse those, 3 squared is 9, which is not 8. So this will kill the argument swapping mutants. Better yet, 2 plus 3 is 5, 2 times 3 is 6. Both of those are not 8. So the times and plus mutants stay dead, and we don't get any zombie mutants wandering around, even if this were still our one and only test. With these inputs, the correct operation is the only simple common one that gets us the correct answer. This isn't the only solution, though. We could have used 2 to the 5th, 3 squared, 3 to the 5th, vice versa, and infinitely more. Even if we stuck to single digits, there are lots of ways to skin that flurkin. This may make mutation testing sound simple, but this was a downright trivial example, so it was very easy to select inputs to make pretty much any mutant within reason return a different value from the original code. So let's look at a more complex example. Suppose we have a function to send a message, like so. Send message uses send bytes to send as many bytes as send bytes can, similar to how much would a woodchuck would chuck, looping over and over until it's done, picking up where it left off each time. It's a very common pattern in communication software. Now, a mutation testing tool could make gazillions of mutants out of something like this, but one of particular interest would be this, an example of removing a loop control. And that would make the code effectively read like this. Now, suppose that this mutant does indeed survive our test suite, which consists mostly of this. There's a little more that I'm not going to show you quite yet, dealing with setting the size and actually creating the message. But even without seeing that, what is this non-looping mutant trying to tell us? If There we go. If a mutant that only goes through that loop once acts the same as our normal code, as far as our tests can tell, then that means that our tests are only making our function go through that loop once. So what does that mean? You'll find that interpreting what mutants are trying to tell you involves a lot of asking, so what does that mean? Often deeply recursively. In this case, it means we're not testing sending a message larger than send bytes can handle in one chunk. Now, there's a lot of ways that can happen, but the most likely cause is that we simply didn't use a big enough message. For instance, here we see in our network module that the max chunk size, what send bytes can handle in one chunk, is 10,000 bytes, and yet we're only testing with an itty-bitty little 3-byte message. Maybe 4 if we have a null terminator, a little more depending how it's serialized, but almost certainly nowhere near 10,000. So what do? The obvious fix is to just use a larger message, larger than our maximum chunk size. We can easily construct one as shown here. Just take our chunk size, we can add 1, we can double it, whatever we want to do to get a bigger number and make that big a message. But perhaps, to paraphrase Shakespeare, the fault, dear Melbourne, is not in our tests, but in our code that these mutants are survivors. Maybe we did test with the largest permissible message out of a set of predefined messages, or at least message sizes. For instance, here we have small and large message sizes, and we tested with a large, and yet the mutant survives. What could possibly be wrong with that? What is this mutant trying to tell us in this case? In this scenario, it's trying to tell us that a version of send message with the looping removed will do the job just fine. If we remove the looping, we wind up with this code I showed you earlier. And if we run our mutation testing tool on that, then it'll show a lot of other stuff as being now redundant because it was only there to support the looping. And if we remove that and lather, rinse, repeat, then we eventually wind up with this. And now the message is crystal clear. That send message may well be redundant. We can just use send bytes directly. Now, it may not be redundant because we may need some error handling or logging or whatever in send message that isn't in send bytes, but at the very least, the looping was redundant. Fortunately, when it's this kind of problem with unreachable or redundant code, the solution is very easy. Just remove whatever it was that the mutant didn't have. That will also make our code more maintainable by getting rid of useless cruft that's just getting in the way of fully understanding everything. Now that we've seen some different examples of spotting bad tests and redundant code, I'd like to address a few occasionally asked questions. I think mutation testing is still rare enough that there aren't any really frequently asked questions. First off, this whole idea seems pretty weird, making the tests fail in order to prove that the code succeeds. Where did this bizarro idea come from in the first place? Mutation testing has a surprisingly long history, at least in the context of computers. It was first proposed in Richard Lipton's term paper in 1971, a paper titled Fault Diagnosis of Computer Programs at Carnegie Mellon University. The first tool didn't appear until 1980 as part of Timothy Budd's PhD work at Yale University. But even then, it was still not practical for most of us with consumer or even developer-grade machines. Not until the past couple decades or so, with advances in CPU speed, and multi-core CPUs, and larger and cheaper memory, and so forth. And that leads us to the next question. Why is it so CPU intensive? To answer that, we need to do some math, but don't worry, it's fairly basic. Suppose our functions have on average 10 lines, and each line has about 5 places where it can be changed to about 20 different alternatives. That works out to about 1,000 mutants per function. And for each one, we'll have to run somewhere between one of the function's applicable tests, if we get real lucky and kill it on the first shot, all the way up to all of the function's tests, if we kill it on the last shot, or worse yet, it survives. Suppose we wind up running just 1/10 of the function's tests on average. Since we start with 1,000 mutants, that still winds up to be 100 times the test runs as compared to just running our test suite. So if our test suite normally takes a zippy 10 seconds, then with these assumptions, mutation testing will take about 1,000 seconds. That might not sound like much because I'm saying seconds, but do the math and it's almost 17 minutes. I don't know about you, but I don't want to sit around for that. But there is some good news. Over the past decade or so, there's been a lot of research on trimming down the mutant horde, but mainly by weeding out those that are redundant with another mutant or semantically equivalent to the original code, or trivial in other ways like raising an obvious error condition. And that has trimmed it down to about 1/3. But even with that rare level of success, it's still no silver bullet, because that takes a lot of CPU time itself, and there's still a lot of mutants left over. The next question is, when creating each mutant, why change it in only one way? There are multiple reasons. First off, the main philosophical underpinning of mutation testing is the competent programmer hypothesis. So let's put that to a quick check. Raise your hand if you're competent. I'm seeing a couple hands out there. So I think the rest of you need to read up on imposter syndrome. Okay. But anyway, what is the competent programmer hypothesis? It's basically the idea that we programmers usually have a pretty good idea what we're doing most of the time. And when we make a mistake, it's usually just one small mistake, like a typo, or adding when we should subtract, or comparing with less than or equal to when we should be doing just strictly less than, or maybe we got it backwards and we should be doing greater than. Does this type of substitution sound familiar? Yeah, it's exactly the sort of thing that a mutation testing tool does. So you can think of it as sort of a did you mean function, kind of like when Google says, did you mean to search for this other thing? Because I don't know nothing about what you were already searching on. There are also some practical considerations. For one, just using one mutation per mutant helps us humans focus. It makes it a lot easier to tell what a mutant is trying to tell us if we're only talking about one thing in the first place. Another reason is that multiple changes may balance each other out. You might remember that first simple example, and it's argument swapping mutants. If one mutant had both of those mutations, the first would swap them and the second would swap them right back for no net effect, so it would survive any test you care to throw at it. And lastly, allowing multiple mutations would create a combinatorial explosion of mutants, with the tool making orders of magnitude more mutants per function. I'll spare you the math, but with our previous assumptions, including weeding the mutants down to about 1/3 at each step, with one mutation per mutant, we'd have about 333 mutants per function, and 1/3, but I'm rounding. With 2, we'd already have almost 110,000, and with 3, we'd have over 35 million. Never mind running the tests, just creating the mutants would get to be a heavy workload, but we can save ourselves that heavy workload and the false alarms and the lack of focus if we just limit it to one mutation per mutant. The next question is, it sounds like mutation testing only helps us make sure that our test suite as a whole is high quality. Is there any way it can help us assess the quality of individual tests? And yes, there is, but it would take a lot longer, and I don't think any of the current tools actually give us all the information we would need, let alone packaged easily so that we could read it in and analyze it. You may remember that I said before, when a mutant makes a test fail, it's marked killed, we stop running tests against it and move on to the next one. So when we're done with a given function, we wind up with a chart that looks more or less like that. If we were to run the rest of the tests, all those blank cells there, that would give us a lot more information that we could put to use, including to assess some individual tests. For instance, look at tests number 4 and 9. They don't kill any mutants. Now, this doesn't mean that they're necessarily bad tests, but it means they might merit a closer look. We can think of it like a code smell. We could look next at those that only stop 1 mutant, then those that only stop 2, and so on, but I think that would quickly reach a point of diminishing returns, probably at 1. And this in turn raises the question of, could we use such a complete report to improve the quality of our test suite as a whole again? And as you may have guessed, yes, we probably could if we had all that information. We could look at the pairs or larger sets of tests that stop exactly the same set of mutants. For instance, you can look at tests 1 and 2 and tests 3 and 7 together and decide if we need to keep both of the ones in each pair. Maybe tests 1 and 2 are testing different important aspects that just happen to stop the same mutants, but it could be that 3 and 7 are essentially testing the same thing and we can get rid of one of them, not because of low mutant stopping power or other poor quality of either test, but because of redundancy between them. That would at least make our test suite smaller and faster. And the last question is, mutation testing assumes that we already have tests, but what if we don't? Can it be of any use then? Well, first of all, whoever built a substantial production code base without any tests needs some educating, maybe with a clue by 4. But yes, mutation testing can help us build our test suite in the first place. We can start with a meaningless test and run our tool. We'll probably get a lot of mutants, including a lot of duplicates, telling us about more or less the same problem, especially since any basically viable mutant will, of course, survive our meaningless test. Then for each function with surviving mutants, we can just pick one. We can pick it randomly, no need to overthink it. Try to kill it by adding a test. Then do likewise to the next function, and once we're all through the functions, we can run our tool again and lather, rinse, repeat as needed. Now, this won't guarantee that we wind up with a great test suite. A lot of code might well stay untested, but this will get us off to a decent start. Then we can look at what's still untested, write some tests that cover those. And at this point, never mind computer science theory, just psychologically, filling in the gaps will be a much less daunting task than writing our whole test suite from scratch. To summarize at last, mutation testing is a powerful technique to ensure that our code is meaningful and our tests are strict. It's pretty easy to get started with in terms of things like setting up the tools and annotating our tests if need be, which might be tedious, but at least it should be easy. But it's not all that easy to interpret the results, nor is it easy on the CPU. But even if these particular drawbacks mean it might not be a good fit for the projects we have going at the moment, I still think it's just a really cool idea in a geeky kind of way. If you'd like to try mutation testing for yourself, here's a list of tools for some popular languages and platforms and some other ones. I doubt many of you are doing Fortran 77 these days. Just be aware that many of these are outdated. I don't know or follow quite all of these languages and platforms, let alone the tools, but the ones I know are outdated are crossed out. There's also a promising tool called Roodle Test, which is a language-independent mutation testing engine that you can use to make language-specific mutation testing tools. I haven't actually used it myself, so I can't speak to whether it lives up to the hype, but I like the concept. So is everybody done taking pictures? Okay, before Q&A, I'll give a shout out to TopTal, a consulting network I'm in that has a speakers network that helped me prepare and practice this presentation. Please use that referral link if you want to hire us or join us. The anchor part tells them it's me and we both get some bounty. And now it's your turn. If you think of any questions later, I'll be around for the rest of the conference, or if that's too late, then there's my contact information and the URL for the slides with more or less complete script. So, any questions? Yes? And then Twitter and LinkedIn and so forth. I have a number of searches that I do on a periodic basis, daily, weekly, whatever. One of them being on mutation testing. When I started doing this about 3 years ago or so, the mutation testing search on Twitter would generally come up with nothing new for several days at a time, sometimes even a week. Now there's usually several mentions of mutation testing per day. And that's not even counting the ones that mean it in the biological sense. So I'd say it's getting quite a lot of notice over the past few years. Any more questions? We have a good bit of time, about 12 minutes.
Can you just describe where, like, you're at the computer coding for the day, whereabouts does it fit in for you? Do you do it test during? Do you do test at the end? Is it kind of all the, like, how does it fall into your coding flow?
Okay, that depends on whether you decide to tell it to test just some little slice or you want to test some bigger chunk. I think probably the easiest way to incorporate it into your flow would be when you're done with some major chunk, like if your group decides that tickets should be a day or less of work, then after each ticket, before you put in your pull request or whatever your process uses, just make it one of the various tools you use to make sure that it's ready to roll. I typically run things like a style checker, other sort of static analysis things, and I would put mutation testing in that category. And if it winds up with a significant number, at least, of surviving mutants that are obviously not false alarms, okay, it needs a little more work. Okay, does that answer your question?
Perfect.
Okay, thank you. Anything else? Going once, going twice. All right, I guess we're sold. Thank you.